1 sec. I'm just going to check that we're up. Come on, OBS. It says it's streaming. Ah, there we go. Okay, cool. Yeah, so welcome everyone. I think this is our 4th workshop so far. We've had talks on sort of personal OPSEC from Strider. So if you're kind of always looking to learn how to stay safe in the space and not get wrecked, that's a really, really good deep dive into some personal security advice, and also like an interesting questionnaire and quiz to take there to try and manage your personal security. We've had talks on sort of personal My bad, I had it playing in the background as well. So yeah, the first one on personal OPSEC from Strider is really, really good. If you want to know how to stay safe in the space, go check it out. Second was from Daiwa about permanently deploying React front ends to Arweave, which was also super cool. I learned a lot there about how Arweave works, having not had a chance to kind of dive into it, but again, really, really practical. And then last week we had Andreas, who's with us today. Say hi, Andreas.
Hi guys.
How you doing?
All good.
Ooh.
Ready to hopefully not milk brains like last time, but ready.
Ready. I like it, mate. The knowledge bombs dropped last time were pretty big, so I'm looking forward to this one today again. So the last week's was about, I think the title of the talk, correct me if I'm wrong, was how Ethereum as a world database stores data, right?
Yep.
And mostly what we were going into was theory around that. Do you want to give people a real super quick summary of the concepts that were there in terms of like just what they were? You don't necessarily have to dive into them because people can go check out the video in their own time.
Yeah, absolutely. The fundamental 3 sections that we discussed was the recursive length prefix, the RLP encoding system that is custom to Ethereum for encoding information. We looked over sort of tries and Radix tries and Merkle Patricia tries as an abstract concept, and then we dived into Merkle Patricia tries as used through the library Ethereum JS. Today we're gonna do a little review of some concepts, but I won't. I'm not gonna torture you with all that RLP stuff like last time, but we're gonna look at some stuff from the previous one, and then we are going to start actually applying it to the blockchain itself and seeing how it all comes together in a more practical sense with the information that we actually have in the blockchain. And I'm ready to go. Shall I head off? We start?
Yeah, man, this sounds great. Just on one thing, on tries, I think you asked this last week. I always assumed it was Merkle trees. Is it tries, or are we saying the wrong?
I am completely on. I have no idea. I keep bouncing back and forth between the two. The name try is actually the 4 middle letters of the word retrieve, because the whole that whole system is it's a retrieval system. It's a data location system. So maybe it's supposed to be tree. It sounds like it's read as try. Who knows?
Eddie's saying Vitalik says tries. So if the Lord's spoken, I guess we the question is answered.
Yeah, I apologize if I keep bouncing back to trees. I keep bouncing between the two. I'm not sure which one to use.
Okay, cool. And just before you go, like last time, if people have questions, you're totally up for people either jumping up and asking them out loud, or I can keep an eye on the chat for you, right?
Yeah, absolutely. If I pause, I'm confused is a legitimate sort of stopping point. If there's something that you just missed or that you feel I didn't explain well enough, just jump in. Don't just sit there in silence. I will add that some of the things that I'm going to be talking about assume that you were here last time or watched it because they're going to be quite a bit general. Having said that, I'm open to being interrupted at any point.
Cool. Awesome. I love it. And if anyone can't speak, just drop it in the chat and I'll keep an eye on it for Andreas so he can focus on what he's doing. So I guess enough chitter chatter, mate. Thanks for doing this again. And over to you.
Okay. All right, guys. Let's get to it. Very all right. Just as a bit of a review, so that we kind of have some of the fundamental concepts in place as we start talking about the blockchain in a more general sense. You are just again to remind you that all the stuff that we're talking about at the core, they're really based around this concept of recursion, and recursive functions that are effectively calling themselves, and as a result have this really interesting property of building up these nested structures, these tree-like structures, which are the fundamentals building block of the Trie architecture that we talked about last week, and also is can alternatively be used as a way of taking nested structures like the one below, and serializing it, encoding it into a linear pattern that still contains all the information in a more compact way. And although it isn't included in this README, you can also write a recursive function which is effectively would take this type of string and it would decode it back into its that nested original structure. And we spoke about those in terms of the radix tree, the Patricia tree, the Merkle Patricia tree, and obviously the RLP encoding system as well. Just as a quick reminder about RLP, RLP is a set of 6 rules. We won't go over them now. They aren't complicated. Once you learn them, and it effectively is taking byte information that is either as a series or a string of bytes, such as this one, or lists of byte items, or arrays, effectively that look like this. They take this format and they get serialized into a linear set of effectively byte instructions that you can then decode back into these nested structures that we see over here. We kind of, I'm going to pick up from kind of around the end of where we left off in the last workshop. Specifically, I accidentally skipped a commit, and I'm gonna use this commit as a reminder of Merkle trees, and how how they're formed and all that stuff. To just as a quick reminder, going back to, I hope everyone can see the screen, but I might have to actually increase the size of it so it's legible on the code as well. This is the best diagram that considered on the internet that describes the custom Ethereum modified Merkle Patricia tree architecture. And we exhaustively, I hope, went through the idea that there's effectively three types of nodes that can exist inside these trees. One being the extension node, the other being the branch node, and the other one being the leaf node. And all those are constructed in such a way that you get this optimal um, optimal structure, which will allow you to locate information. Um, the commit that I skipped in the last talk.
Andreas, do you want to zoom in a
Yes,
little bit on the code?
absolutely. Um, take it up
Uh,
that
that
much, or can
I,
I go one down? Is that
I, I think you're probably going to need it at that.
okay? Okay, okay,
Yeah.
okay, okay. Look at this. Um, So jumping off, we were using the Ethereum JS Trie library to start building up Trie structures, and then placing them inside a level DB database, and seeing what the um what the relationship was between the database and this Trie structure interface that was putting stuff into the database. And we're gonna do that now one time, just to refresh on what that looks like. Specifically in the code example, we're gonna add two pieces of data to the Trie. And it it's if you were here last time, I hope you have a idea of what the key is and the value, etc. Specifically, if you look at the keys that we're about to put into the Trie, you'll notice that uh, both of them start with the nibbles A B, and then they veer off into different data. So um, we just run that. So again, just a quick refresher. We're using some of the methods. We're currently using the lookup node, which, to put into a better context, that from last week, lookup node is uh, is is accepting a hash value, which then internally in the library it goes off into the database and says, give me the information that's sitting that you are holding under this key value, which is the root. And then, being provided with that information, it reconstructs the Trie tree at that point, and then spits it out as a JavaScript instance for us. And these two elements that we're putting into the Trie return this this structure over here. The What we hadn't looked at last week, we ended up on seeing a structure that was a branch node with a couple of leaf nodes. Because these two values because these two values both start with AB, internally the MPT library figures that out, and knows that this is an opportunity to use the extension node, right? The extension node and the leaf node have these extra these new effective nodes that are added to the MPT library, which allow us to shortcut information so that we can keep the database smaller. It doesn't take up as much memory. And already, if you look at the extension node, you'll notice that the nibbles that it's shortcutting are in decimal 10 and 11, which in hex equate to AB. The value, the value stored in the extension node is actually a branch. It's a branch node, and if you remember from last week, you might notice that the branch node is actually expressed in raw format, in the format that the method raw prints out. Raw being the format that has the hex prefix in it, all the clever prefixes which let the that embed inside the database entry that what the structure is of the trie that it is part of. But and the raw format is the stage that we arrive at before we RLP encode it, and and um and add that sort of like nested, serialized, nested structure. Um, so, and what's interesting to just remember is that if you have an extension node, it will always, the next node, which actually inside the library is represented by the value, will always be a branch. You'll never have an extension node with a value as a leaf, because though effectively that means that they're both just shortcutting information. It can all just be expressed by one leaf. It doesn't need the extension node. So the extension node will always point to a branch, and in this case, this branch has it has values in the index of I think 11 and 12, which represents C and D. Then internally, you can see in the RLP encoded format, if you remember from last time, the hex prefixing over here is saying I am a leaf node and I have an odd number of nibbles because it's 3, right? Like if the hex prefix was 2, it would be indicating that there was a couple of nibbles after it, an even number of nibbles after it, rather. And then you have the value. So this JavaScript instance that we're looking at over here, which is the extension node with a branch in the value, and then the leaves, sort of equates to seeing like it equates to this part. Imagine if this was the root. It's like an extension, a branch, and 2 leaves. This is the kind of architecture we're looking at. Then underneath it, we have the serialized format of the node. So taking all that raw hex prefix data and spitting it out as as RLP data. And if you we can just roughly go over it now, but just as a reminder, like maybe I'll just open if I was a decoder, if I was code that was parsing this, I would know. I would say, okay, I see that this prefix value is in the range of rule 5, which is the list value, and then it has added to it the length of the byte string. So it says, okay, I'm creating a list. It comes to the first item. It sees in the first item that this is
Andreas,
yes.
Eddie asked, "What's a nibble again? Is it a byte in hex?"
A nibble is half a byte. So if a byte is expressed, imagine that the number, the value 255 is expressed in byte format. You could express it as FF. A nibble is just 1F, and it's basically the values 1 through 15. And in the context of what we're adding into the tries, if you just imagine for a second that instead of ABCD, this was an Ethereum account and it was all just hex values. When we're talking about nibbles, we're talking about just one individual part of the path. I hope that makes sense. And so, for instance, inside the branch, the nibble is parsed into its decimal form, so we can stick it into the right place on the branch. If you remember from the stuff from the radix tree stuff we were looking at last week. I hope that answered your question. Going back, just really quickly, really roughly, we know that since we're parsing this as an RLP, decoding it as RLP, I see this number, I know this is part of rule 3. It's telling me this is an item. It's followed by 2 bytes. Then we look at the first byte, we see it's double O, and now because the library, which is RLP decoding this information, is a trie library. It knows, it's like, okay, I've just seen 0, 0, so this is obviously a leaf node. No, sorry, an extension node. and it has an even number of bytes followed by it, and those bytes are the bytes AB. So that was the first that was the first item in our array. Then we know that's the first item in the array because we finished reading the hex prefix to decode that item. So then we come to the second item, which is the value 80, 80, 80, 80, uh in RLP means an empty value. It's rule 2, and it's an empty value. So we basically have a series of these empty values. We get to C2. C2 is again, it's like rule 5. It means it's an array. It only has two elements. It is only followed by 2 bytes. Then we come in, and because we're a trie or library, we see the 3. We know that this is a leaf node, and it's a leaf node that has an odd number of nibbles, and the nibble is D, and then followed by the value 0, 1. I won't go any further, but hopefully, if you can kind of understand this as pseudocode, you can see extension node. The shortcut is AB. Its value is a branch because it has all these sort of empty values in it. At some point, we have a leaf node. Its shortcut is just the value D, and then its shortcut is only the nibble D, and then we see the value. And like, hopefully you can start to see that inside this JavaScript instance. So basically, what I put you through that hell again, okay, yeah, another reminder, just to refresh you from last time. The 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 hashed value of that serialized byte array is this value over here. And because we're also printing out the database in this file, you can see keys, and you can see values. And if you look at this key, it equates to the hash of the value of the RLP encoded value, and the value is that RLP encoded value. So basically, this is just that was a refresher to remember extension nodes, branches, and leaves, and also to drive into your head the idea that in the database, that really there is no tree. The trie is a library, or it's some code which is organizing the data. The trie information is actually baked into the information itself. So when a trie library requests, like, let's say by setting the root to this hash over here, and it gets sent back this information, the trie library itself reads this information so that it will be able to reconstruct the trie as in code. So the it's just to kind of to drive that idea but into your head, the trie is actually baked into the data itself. Okay. And also, just a quick reminder, this was like this really dumbed down example of how that Ethereum, through this type of architecture, it has the quality of history. So you can basically, like, obviously this is a very, 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 very small trie. There will always be much more complex than this. But since since the whole thing was expressed in just one in just one structure, that's our root. Okay, so basically this is just a reminder that if you switch roots, because the trie information is baked into the information on the database, that's how you get like a commit history. That's how the blockchain lets you go back historically and see stuff at a previous block, and stuff like that. Those are those general ideas that we kind of got to at the end of the last workshop. So am I saying like? I hope not. I couldn't tell that I was doing it last time. Someone call me out if I keep saying like. Okay. The intro, where are we at? Complex trie with hashed values. Okay, so again, quickly, we did look at this last time, but we'll just look at it again. This is now creating somewhat more complicated trie structure. Okay, and we're more or less doing the same stuff. Actually, no, we're not. Now I'm going to talk about it a little bit, but let me just run it. So as we can see, things have gotten more complicated. Just with the 4 elements, we've ended up with more branches, more extension nodes and stuff. But what I wanted to just bring back to your attention is, as information gets more verbose in terms of byte data, what the Ethereum Merkle Patricia tree does, Trie, it will take if it sees that there's data from the database which is more than 32 bytes long, it will hash that information. It will stick it in the database with the key as the hash and that data as the value, and it will stick that hash into the position that we would normally expect to see the sort of raw format. What does that kind of practically mean? What it practically means is, and I've kind of done it over here just to show you is, I mean, you can do it either through lookup node, but what it's effectively saying is I've reached the hash. Can get it for me from the database so I can continue building the trie. So in this case, I'm using get on the database. I'm doing, and I'm also doing it over here with by using trie lookup node, which is doing effectively the same thing behind the scenes, and I'm getting that next bit. So basically, what it does is it starts to break up the trie into multiple database entries that need to be read sequentially to construct that trie architecture. Uh, that was that. So just that little bit to remind you of the fact that it adds those hashed values. And did I not save the other? Don't tell me. Okay, but let's go see what this is. All right, I seem to have not committed a commit, so I'm gonna have to just say this to you. There is 2 types of trie, and they're basically both available in this in the Ethereum JS library. We've been using trie all the time. The other one is called secure trie. The only way that it differs, and I'm gonna just kind of mash up this code to show it to you. The only way that it differs is if instead of instantiating trie, I instantiated secure trie. The only way it differs is behind the scenes. When you input a key into it, behind the scenes it hashes it before it commits it to the trie database. So everything ends up looking like this. Every single entry ends up looking like these hashed values that in the normal trie it only does it if it's larger than 32 bytes. Why does that exist? I haven't fully grokked it, but I'm gonna tell it to you as it's been explained to me, and we're all gonna have to take it as gospel. The secure trie is used, and we're gonna talk about the different tries that exist in the Ethereum database in a bit. It is used as a way to prevent denial of service attacks on the blockchain. It makes it computationally unfeasible to really try to slow down all the in-out operations on the blockchain. It kind of is almost like a mining. It forces someone who's trying to attack the blockchain by through a denial of service attack. It makes it have to do a certain level of mining, so to speak. Okay, that's as much as I understand it at this point. So that's all I'm gonna be able to tell you. Anyway, so very quickly, the last commit in the Merkle Patricia Tree branch. Okay, we're gonna look at it very. Is that it? Yes. Okay. We're gonna look at it roughly, but I just the last commit is just so that you can see all the interesting methods that exist on this on the library. Okay, so we've been looking at lookup node. If you were here for the last workshop, you saw that we kind of had we used the get in the custom one we built. This find path again that was used in the custom one. In this, just so that you can so that you can see the oh no, sorry, this is getting messy. Just so you can see it. What? No. Did I not save that? Do it again. Okay, just so you can see that this this did I accidentally go to something else? Okay, guys, sorry. Let me just
Andreas, it might be the you imported the secure try at the top.
oh yeah, okay. Git check out course go see where we're at.
Yeah, so you had you know when you're instantiating a new try class,
Yeah.
you had changed that to secure try.
Yeah, I think yeah, I just forced it back to the commit, so we're good. Okay, so basically how are we doing for time? Because we haven't even gotten to the other stuff. All right. Really quickly, this is the output of the find path. It's much more complicated than with the custom one that we were working with. It gives you a lot of information, like what was the stack of the stack, what was the path it went down, how many branches it went down, and extension nodes, etc. Trying to find what you're looking for. And the other really interesting the thing that the library has is this method and also and also a class of its own. This method uses that class inside. This method uses that class inside, but basically this is a way to walk the whole try structure. You know, instead of the lookup node or find path, you can use this and you can create your own custom instructions in here so that it can crawl the whole try and find stuff for you. It's this is the last commit in the Merkle Patricia Tree tribe branch. If you want to go, I've left some notes in there. You can go and mess around and see what kind of stuff you can do. And one last thing, really quickly, and then we move on because I'm sure um, it there's one method underneath here that effectively I wanted to, again, I'm driving home that idea of history. I'm actually putting the same key into the try every time, but I'm changing the value inside there. Okay, now then basically what I'm doing is I'm iterating over the database itself, like everything that was printed out in the database. You can see here, and I'm collecting the key, and I'm copying the try because you can't instantiate a new try. It has something to do with it has something to do with the level DB database. I'm copying the try instance. I'm setting the root to the key, setting the root property, which is a getter and setter, is the same almost as looking up the node. And then on the try, I'm getting that value each time, and you can see down here that the values are 3, 1, 2, 4. So this is just to hammer home the idea that you can that tries are in part they're a historic mechanism as well. Okay, that's done. Let's move on to new stuff. So Ethereum. All this time, it's all just been about the library. Uh, you, I'm sure everyone is familiar with downloading blocks from, with an RPC, using an RPC request. There's this is what you get if you ask for the sort of like minimal information of a block, like of a full block, the header plus the body, right? It looks like this, and this is what it looks like. This is what it looks like if you ask for or the full block in its most verbose sense. And the difference is that one has the transaction hashes, the other one has literally all the information inside the transaction. What's interesting is in the header, you will see that we've got these things. We've got a state root, we have a receipt root, we have where's the transaction root? Somewhere in here there's a transaction root. Oh, transaction root, there we go. Transaction root. These are effectively the roots that if we supply to a trie that's communicating, that's hooked up to the database, will provide us with the information that from the blockchain as it was at that moment in time on the blockchain. Um, so I'm sure you knew that already, but
So, Andreas, if someone passed that transaction route into the Trie library, you'd get all of the transaction data from that block.
Yes, but no, wait, not on the library as we have it, because you have to be a full node that has downloaded all 300 plus gigabytes worth of level DB key storage data, so that you would be able to do that. So we can't do that right now, but if you were a full node, you would. Um, uh, yeah, that is that. But you were correct in that assumption. So uh, to go back, this is a bit rough, but it does explain what we need. If you imagine this is
zoom in once.
Oh yeah. Sorry. If you imagine that this box is the block that we just downloaded, you can see you got the transaction root, you got the state root, the receipt root, and these you can see now. You should have this kind of idea in your head of what this means. That the transaction trie is how you would interface with the database to either to maybe prove that this root, which is what we're going to do. There is a fourth trie, the storage trie. The storage trie, to get to it, is in a state root. You have in a state root. Maybe I'm not going to tell you that yet. I'm going to get to that. So I'm not going to explain to you why, but just now for to know that there is another trie, and it's connected to the state trie. In fact, actually, a few things to discuss now, because we were talking about that secure tree. The state trie uses that secure trie format where everything's hashed. The storage trie uses the secure hashed format. The transaction trie and the receipt trie don't. They just use that the trie that we were using all this time, where the key isn't hashed before it's added to the trie. Another thing which took me a while to wrap my head around is that there are multiple transaction tries, there are multiple receipt tries, there are multiple storage tries. There's only one state trie. And what that means, and that confused me for a long time, but what it basically means is it doesn't actually mean that there's instantiated tries. It means that the state trie, every time you add to it, you are accessing the information from the state trie in its previous format and modifying it. For you're also doing that for the storage trie, actually, but there's also multiple storage tries, because there's actually one associated to every single account. Transaction tries, every time you build a transaction trie, you start from scratch. You don't need the previous transactions to build it. You're using you're creating an instance of the interface so that you can put everything into the database in such a way that you could just read it in this one try. So basically, it's trying to hammer that idea home that in a way the tries don't exist. The tries exist as RLP information inside the values in the database, and then you use tried libraries to recode that into something that's usable in a programmatic sense. I hope everyone's still with me, and if you're not, just let me know. You when I'm gonna get I'm this my now after this workshop where I'm gonna get back to it, and I'm going to put all this information into the repo like as references. I haven't done it yet, but you will see if you go off and you do your own sort of reading about this stuff, you'll encounter this really good diagram that really kind of shows you the whole process of the EVM, about how it works. And as far as we're concerned, we're not going to touch any of this stuff, but you can you can see here there's information. There's a lot of information over here about the state tree, the transaction tree, what the values that go into it. As we go on, this diagram will make sense. But this is actually a really good diagram. So let's jump into the transaction try. I feel like we're behind. I'm gonna keep you guys here for a while again, I think. Sorry. Or we can break it up actually. Okay, transaction try. So what do we go to the first proof transaction route? The commits work from bottom to top if you go through them. Okay, so basically, first things first, like in this, we're using a new Ethereum JS library. It's called TX transaction. Okay, it has a lot of it has a lot of helper classes with a lot of useful functions, and we're gonna go through it. Well, it's worth taking a look at. So basically, what we're gonna do in this example, and this is a fully working example, you can come back on your own time and you can mess with stuff. You can add, you can maybe walk through the tree. You can inspect it, but basically, what? Sorry, just the one. Sorry. No, sorry. I didn't put the stuff in package.js. Um. Okay, so all right, all it's printing out is letting us know that the transaction route in the block, what we are doing is we are using we're using ethers. We're using the provider from ethers. We're requesting we instead of using get block, because that kind of it's a helper function, but it doesn't provide you with all the information. We're using the send method, and we're doing the RPC request directly. We're retrieving the block information, okay, in the block. Then we're taking the block information, we're going into the transactions array, and we're mapping over everything. And we are reconstructing the try to and proving that the root of our sort of local try matches the transaction route which is embedded in the blockchain. So a few things like up here, and this happens a few times in when you're working from library to library. There's some syntax changes about how things are expressed in the libraries and how they're expressed in at least when you're pulling stuff from Infura. So for instance, in the block that Infura gives you back, input is expected as data, as it is also on ethers JS. It's the input property is expected as data. The gas property is expected as gas limit. So those those changes are being made on the transaction. Then, according to what the transaction type is, and we're gonna talk about this. We're instantiating one of the classes, one of the classes from Ethers.js, and we're serializing the transaction. What does serialize mean? It's very similar to the idea of serialize in the Trie library, in the sense that it's RLP encoding plus it's doing a little bit extra. So in the Trie library, it was doing the hex prefixing. In this library, it's adding some type data, and I'll show you what that is. I'll show you what that is. But effectively, you can see that it works. Okay, it works, and if you wanted to, you could come in and you could inspect this Trie structure. But we're gonna move on because there's more. All right. No. I'll save. Okay. Same code. Nothing's changing. We're just gonna input more information. Another little quirk. The in from Infura, when there's some information that comes back and it's expressed as 0x0. However, when building the Trie, that information 0x0 is in the Ethereum JS RLP library. The value 0x0 equates to through the rules that has this set up, it equates to the value 0, which is correct. But what it's expecting is for it to be an empty value for the Trie to work. So I'll kind of show you that in code real quick. But the thing is, I shouldn't waste too much time on this, because you can if you can go in and look at this stuff alone. But basically, what's important, and I didn't show you in the last time, it's the signature that you have to use to put information into the Trie library, and specifically, it's the RLP encoded version of the transaction index, what was its index inside that transaction array, and the value that you put in is that serialized value. And I'm basically over here, I'm printing those out so that you can see them in this code that I've committed. I have two example blocks. I have a small block and I have a large block. The small block just happened to have 4 transactions in it, so it's much easier to grok through the Trie and see what it is. The large one has a lot more information, so if you want to investigate it, you can. Um, the buffer, so the RLP encoded the key effectively is stuff like buffer from hmm is it in here, transaction, the RLP encoded index, the RLP encoded transaction, the RLP encoded index, buffer from RLP encode 0 is 02. Yeah, okay. They don't require, they're in that rule 1 range. They don't require an extra hex unless you get to a value. Say in a normal transaction, in a normal block, you might have 200 transactions. So when values start going above 127 in hex, they will receive an RLP encoding. I might show you that real quick, just so you can see the difference of what like a large block looks like. I'll just run it again. This is the first time that we have seen a value put into a Trie, which is more like Ethereum. Like, you see, like this value, you can see it starts with F8. This is RLP encoded. This is all the transaction data. So all this time we've been just using like the value 0 or 1 or something like that, 0 1 0 2 or whatever. Now we're starting to see real Ethereum data. This is a transaction where if we RLP decode it will become an array with a set of values, and we're gonna do that in a second. Very quickly, I've added I've added a large block. I'm just gonna run it one more time. Okay, there you go. Look at the, like, we're just looking at that. This is the structure: leaf, branch node, leaf node, leaf node. By the way, I'm using the walk tree method on the tree to do this. So you can come and you can play with this in here as well if you want. Already, as we got to the bottom, you can see this was the buffer that's used as a key. It has RLP encoding. It's no longer just 1 byte. It's 81 D3. In fact, they're all going to be 81 because nothing exceeds 1 byte. So what does that really mean? It means, and I'm not going to show you to encode it. It just means that this trie structure is super shallow. It doesn't go deep. It only goes to a few nibbles down. And all that information is really flat in a transaction tree. So yeah, basically, why did I show you this? It's just for the next commit, so that you can see you can understand a couple of methods that I added. Here we go again. Is everyone there? Can you guys hear me?
Yeah, we can hear you, man.
Okay.
How is everyone following along?
If anyone has questions, I appreciate that this time around it's a bit more vague than the last. I'm hoping that you retained information from the previous one and you're kind of following along, but we're gonna come to some conclusions. And the last one is actually quite interesting. The storage trie. So okay, this commit is called custom serialization. So we're no longer gonna use the Ethereum JS library to do it for us. We're gonna do it in a custom manner. And now I'll be able to show you what that type information was. First of all, we're using the change syntax. We have to do some recursive formatting because one, we have to account for that quirk. So we have to change that value when we need to, and also because transaction type 1, which is, I think it's called the access list transaction type. Let me just show it to you. Let me find one for you. An access list transaction, which has transaction type one. Sure, there's one. Let's start from the beginning. Did I pass?
I don't think there was one, man.
Yeah, I think there is one up here. Sure, there's one in there. We went all the way through. Okay, that's weird. Did I download? I might have downloaded another block. Okay, guys, I'm just gonna have to show you. But the access list information looks something like this. I'm making this up, but it's sort of like account. Well, let's just say that's an account, and then it's some hash information, and then there's another property underneath. Okay, basically it's an array of objects. If you remember, RLP encoding only works on arrays and lists, arrays, and byte strings. So what we need to do is we need to serialize those objects into arrays. So we basically we don't take into consideration the property names, and we just take the values and we stick them into an array. So again, this is sort of an example of how RLP is agnostic. It's agnostic, and it expects you to do the work for it, and it expects you to also know what is going into it so that you can make sense of it. And what the transaction library was doing for us, okay, was effectively internally it was doing what I'm doing manually over here. I've created like a dictionary with some methods which which are different for what type of transaction type it is. The EIP, which explains why what this new transaction type pattern is called EIP 2930, and what it effectively does is it says in front of the RLP information we're gonna stick 1 byte of information, which is a type. It's a byte type, and so far there's only legacy, which doesn't have a byte type in front of it, and it's and inside inside a transaction on the block it's expressed as zero, as zero in hex. We have a byte for 01 and byte 02. Byte 02 is for a EIP. It's for no, it's for a it's for a 1559 transaction, right? The transaction type 2 is called an access list transaction, which I've never seen in the wild. I mean, I've never used in any way. The way what happens is each one has its own signature that needs to be RLP encoded. All this time we've been used to seeing RLP used to sort of to construct trie information, right? But it's also used to encode data that you put into a transaction. But data in a transaction is for the most part flat, except for the access list, which has this access list property that we have to make sure is expressed in an array. So this one is the only one at the moment that's recursive and requires that sort of recursive RLP encoding. But basically, each transaction type has its own signature that needs to be followed, and then and that EIP 2930 does what's called the transaction envelope, which is basically that it sticks that byte value. In the case of a legacy transaction, it does nothing. In the case of a access list transaction, it adds the byte 1 in front of the RLP encoded information, and in an EIP 1559 transaction, it adds a 2 in front of the information. Okay, and basically that's what is happening in this code. Instead of using the transaction library, first we are extracting from the transaction, okay, from the transaction according to what type it is. We're choosing what those methods are going to be. We're then following the signature and outputting just the information that we need for the RLP data. We're encoding it recursively because of that weird thing that with those quirks and the access list. So we're making sure that it's all encodable and ready to be encoded. We're finally RLP encoding it, and then we're using the transaction envelope to stick those bytes on the front. Then we're putting it into the trie. Okay, we're putting the complete serialization as the data, and we're RLP encoding its index inside this transaction array. Okay, so why the hell did I show you all this stuff? First of all, it kind of is it's circular. All we did was we verified that the transaction information that existed in the block is correct by its root. It was completely circular. It had no value really what we just did. So why is the transaction trie and the transaction root valuable in Ethereum? The reason it's valuable is because of the concept of light clients. This information is included on the blockchain, so that a light client, which is one that wants to do information, like for instance, a light client could be a wallet, okay, a wallet application that integrated directly into a phone. Excuse me for a second. a light client isn't going to, if your phone had a light client on it in the future that was part of sort of an inbuilt wallet, for instance, it wouldn't want to download all 300 gigabytes of the full node database. But what it does want to do is it doesn't want to care if it trusts the node that it's going to get the information from the database. What it wants to be able to do is check the information that from the database. So you can request data. If you're a light client, you can request data from a full node saying, I want this transaction, and and then with the information that exists in the blockchain, like the transaction route, you can ask for a proof, which is something that we haven't touched upon. Probably should have, but it's a method. It's more methods on the Merkle Patricia tree. Create proof, I think, and verify proof. You can basically ask for the data, ask for the proof, and then if a light client has a trusted source of the most minimal amount of information that it needs from the blockchain, just the headers, which has the transaction route, the receipt route, the state route, then it doesn't need to trust the database. It will check for itself if that information is important through the type of trying mechanisms that we've been looking at. So that's kind of why that's an example of why the transaction try is this useful component on the blockchain. One more thing to point out to you, which I thought was in here and it isn't, but you're gonna have to trust me just so we can keep moving. But if you were to take the hash of the completely serialized RLP formatted type enveloped data, and if you were to hash that, what you would get is the transaction hash, which is then stored in a transaction. But if all this Merkle tree information is starting to make sense to you, in the database, the key to this serialized information isn't the transaction hash. It's the RLP encoded nested trie structure with all the bytes that show where it is in the trie structure, plus the transaction inside that. So it's a completely different hash. So why is that interesting? The reason that's interesting is you can't say to the database, I have the transaction hash, give me the transaction information. What you have to do is you have to, if in a hypothetical example, you would have to take the transaction hash. You would have to go down block by block by block till you find the transaction hash. Inside that block, you will then find the transaction route. You would then also find what index the transaction is in that block, and then you would use the combination of the index, the transaction route, and the transaction route to get you set your Merkle tree to the root of the transaction route, and then you would RLP encode the index to get that information. That's a lot of work that has to be done to find the transaction. So what does that mean? It means that Geth, and also, for instance, the Ethereum JS developer full node, because the Ethereum JS, all the libraries, they're effectively a JavaScript implementation of a full node. They also, on the side, it's not part of like Ethereum's sort of let's say white yellow paper, but they store that information in a database as well. So they on the side say, for every hash of a transaction, I'm going to store what block it's in, and potentially, for in the case of Ethereum JS for sure, also the index that it's in, so that if someone requests that information, it has a shortcut to find you the actual RLP data inside the database using the Merkle tree. What is interesting about that is it kind of proves how the blockchain is effectively services building on top of each other. That is why, for instance, block explorers are important. They do work like that. They do sort of side work so to make things easier. Indexers, or even the graph protocol, which is like a whole protocol that has its own sort of like tokenomics behind it, which is trying to solve problems such as what are quicker, more effective ways to get to data. Because in some instances, like that one that I just explained, data isn't readily available quickly. It needs external structures that will help kind of get you to that data. So transaction tries. If you want to do what we were doing in workshop 1 and really go in and mess around with what the tries look like, what they look like on the database, this is an opportunity to go through the other branches and reconstruct stuff and look at it yourself. So transaction tries down. Then man, it's awfully quiet. Is everyone still there? And is everyone is anyone lost? And would I'm
I'm keeping up.
no.
I'm keeping up
Okay,
with
okay.
super high level concepts.
Okay,
Yeah,
okay.
yeah. But it's definitely a rabbit hole, man. You're a saint for going down that.
I didn't even finish it. I might have to do another workshop at some point. Okay, so next one, transaction receipt try. How are we doing for time? Just so I can feel the anxiety. How are we really late?
We're an hour and 15 in.
Oh man. Oh, okay, I've gone way over. Okay, sorry guys. We might have to break this up if you guys want to. Okay, fine. If receipt tries, we're not gonna go over this too much. Receipt tries are actually quite easy, and we don't need to spend time on it. Effectively, a tries have we won't even go over the code. It's more or less the same stuff. We have to do that formatting, that to fix some of the little quirks. And this is the RLP signature for storing a receipt into the try. If you run this, you'll see that the receipt root is the same as our local try root. It will come out as the same values, and likewise, when you ask for a transaction receipt, you provide the transaction hash. So everything I was just explaining about how you need these sort of external services, or these sort of parallel sort of database entries, very much apply to the receipts, because you literally need the transaction hash to get to that information instead of going all the way down the blocks. All right, the receipt try out the way. If you want to come and play with that as well, you can. All of it works. They're working. They're working. They're proving the root, and you can come in and play mess with them. So storage try. This is the interesting one. I should have gone quicker through the other information. So first off, I've got a little thing. Basically a store. I'm sure you guys have done this, where you have asked you have done ETH get storage at, right? You've tried to get information from the storage, but all you ever get is one slice of information, one slot of information. There's no way to ask the blockchain through Infura to give you the whole storage try or the whole state try. There's no way to do that. So I basically went digging through Hardhat, and I found where internally it hides its simulated state try and its storage try. So basically, it's over here, and this Node.js file is going to expose it for us. That was like 10 days worth of side quests just right there. But yeah. Anyway, what it basically.
You good, Andres? Oh, we lost him. Dude, if you can hear us, you're frozen. Oh.
Can you hear me?
Yeah, you're back now, mate. Where did you go?
Okay, I don't know how long was I gone for.
About like maybe 10 seconds.
Oh, okay. Did you hear about my side quest to find the storage try and the state try?
Yeah, we got the side quest. You were the bit about Hard Hat trying to find where they were hiding the.
Okay.
Yeah.
So basically, state try and storage tries are now exposed. So as long as you're running an in process network, and you're not forking, or you're not using the hard hat node, you're just doing everything in process, you'll be able to have access to these tries. So, okay, the storage try. This one is the most rather sorry, the state try. Very, very briefly about the state try. The state try is the how basic. The only thing I'll explain to you about the state try, and this is kind of the core of how we get everything in Ethereum. The state try is inside the what is continuously added to the try is the key is an account address, whether it's an externally owned account or a contract account, followed by the RLP encoded nonce, balance, storage root, and code hash. So this is where we went. This is where we saw that storage root try. The way that you can access the storage root, or if you're a full node, is you go down, you get the account address, you put it in as the key, on the state try. You find the RLP encode this RLP encoded information. You decode it, and then you find it. So here you'll see I've taken the storage root for the contract I'm going to show you, and I'm also looking for the contract address on the state try, and then RLP decoding the information. So the reason it's taking so long is because every time it has to compile the contract, and it has to deploy it and everything. So, but here it is. This is the storage root. The fourth element in the decoded RLP information associated with the account, with the contract address. The fourth element is the storage root, and that's what we're gonna look at right now. So okay, introduction to storage. I've created an extremely minimal contract. It has one state variable, all right, one storage variable in it. It's a uint8 of value 1. Okay, so once you deploy a contract, the state variable finds its way into the storage try, represented by that root. Okay, but by that storage root. So I'm on the right. Okay, so I'm sorry, guys. I've taken way too long, so I'm gonna maybe breeze through some of this information and try to give you the general overview. Basically, the format that things get added to the storage trie associated with one specific account is the slot number as 32 bytes, and the value excuse me, the value expressed as the least amount of bytes that it needs. So if we were looking in the database, if we were looking in the level DB database, the key would be it would be the hashed version of this, because it's a secure trie. But effectively, yeah, it's the hashed version of this. So just think of, yeah, because we're dealing with that secure trie, this would be hashed, so it would be like a random 32 bytes of content, and this would be the value in the storage trie. You can see here, actually, you can see, because this one Ethereum, this contract, right, which, by the way, inside when you deploy it, if you remember, it was on the previous branch. The two of the RLP values were, one was storage root and the other one was code hash. When you deploy that contract, the contract code gets stored permanently, immutably in the code hash, and the storage becomes a Merkle tree that represents those storage values. So right now in our contract, we just have this one this one value. That's it, and it's represented in our storage root. So you can see it's the value of 1. The value is 1. This here, because it's only one leaf node, all the nibbles are shortcutted. This is the hashed version of this key. Okay, so basically, and now you can start to see some interesting things that, like, you learn about in Solidity, and you don't really think about in the context of data storage and tries and all that kind of stuff. If I deploy this contract with these values, okay, you can see it's a uint8, it's a uint16, uint32. Deploying. Look, it's done the data packing, because these were not 256 bit values, 256 bits being 32 bytes. If you do all those weird changes, we could stick all these values all into just one. We could stick it in all into just one storage place, and you can see the first one's a uint8. So a uint8 can only go to the number. It can only go up to the number 255, which in hex is FF. So it only needs 1 byte of information. uint16, 4 bytes of information, because it's 255 times 255. Interestingly, uint32 doesn't chop off those values. I mean, it chops off those values because it doesn't actually need to represent this one in particular. So it gets rid of them. It optimizes space. You can see the RLP encoding down here. You can see that it's 84, so it's like four bytes of information, and these bytes of information are the value. Now look what happens if I change it and I just stick a value of 128 in there. Oh, it did. It did manage to put it in. You can see the value of uint 128 took up this space over here. It's still packed. It's still packed in there, in that one sort of slot, in that one Merkle tree key value pair. It's still in there. But now now things look really weird because I put in a uint 56, which needs 32 bytes to express it. Okay, and that now you can see slot 0 only has these two values in it. And actually, if I want to find the next one, I have to look at the next, what is called the next slot. Like basically, slots in Solidity go down linearly. So with not taking into consideration data packing, they go down linearly, and they're expressed in keys in this format. And hold on, let me show it to you in the code. And if I want, if I wanted to now find that next value, I also have to account for the next storage slot. I need to. By the way, if we run over time, we can do this in another session if people want to. So I'm just like putting that on the table. There's no problem in stopping. I'm just gonna keep going until someone asks me to stop. But basically, I now.
Andreas, you've got a question from Sondem in the chat.
So, is this related to the solidity of the market? Yes, yes, yes. The if you've done something like crypto zombies or something, you will have seen that they say to you, take into account data packing. They say, and what data packing means, what you just saw in the code. It means if you're using uint arrays, uint, if you're using values that don't need 32 bytes, clump them together, because inside the database, because inside inside the database, they'll be expressed like this. Okay, all right, and then let me just quickly check something. I did put one. Okay, look. So basically, take my word for it. You can come and check it yourself. I'm doing all this. I'm just kind of checking. I'm making sure everything is padded to 32 bytes and stuff like that. But effectively, what I'm doing is I'm not only looking. I'm not asking. By the way, we're doing that. We're doing the circular thing again of requesting storage from the provider, right, at a key. Okay, that's what we're doing with that, with add storage, and then whatever the value is, we're putting it in our custom trie, because in this example as well, in the previous one, we're checking to make sure every time we're checking to make sure our custom trie root is the same as the one that is stored in the state tree, in the state tree's account storage, if that makes sense, because we have to go down the store. When you do an ETH get storage at, you provide the address and the key. The reason you provide the address is, first it needs to go into the state tree, put the address in as a key, get the RLP encoded information about the storage root, put the key into the storage tree associated to that storage root, and retrieve the data. That's how we're getting the data out, and then we're putting it into our own tree to check if to do things like look at the nodes, which in here we can start doing. Like basically, just to remind you, what I've done is I've added a 256 bit value as a storage variable into our contract. But because it's 256 bytes, it pushed it. It didn't data pack it like it did these two values. It pushed it into a new slot, right? And then in the code, what I basically did was I was like, go into ETH storage and tell me what's in slot 0 and in slot 1. That's what I'm doing down here. And then the output, as you'll see, the output is saying, okay, storage slot 0, you've got these two data packed values. This is where it is inside the our custom storage, reconstructed storage trie. Underneath it, key slot 1. In key slot 1, you've got the value 1, which actually is the stripped down 256 value. It had to be put in a new slot because it couldn't be expressed with other data pack value. I know it's confusing that they strip off the values. They're just doing optimization, but you trust me, in key slot 1, which is which now look what it's done to our Trie. Now it's become a branch. Because it's a secure trie, both of them are, well, these two hashes are the nibbles, basically, right? They're the nibbles. Here it's in decimal, here it's in hex values. So we've already made our trinode, our storage trinode, more complicated. And yeah, basically, I hope you're following what I'm saying. Basically, what's interesting is the fact that variables in a contract, storage contract, how they end up being in these Merkle trees. So that was data packing. Arrays. Oh man, it's so much more information. I think I'll just do the arrays, and if you're brave enough, you can go check out the structs alone. But
You've got how many more topics have you got to cover, dude? You've got arrays, and then what's left?
I've got arrays and structs. Are you guys all good to keep going? Is everyone okay with that?
We'll take a read from the crowd. But you have a question from Sondom, real quick.
Is the slot UN32 in the third slot? Is the slot UN32 in the third slot? Let's have a look at the code. Yes, you're correct. It is in the third slot, but we're not gonna look for it right now. We're gonna move on to some other stuff, which is uh okay. So arrays. Okay, so now we're going back. We're no longer using just uints. We're gonna create an array of uint32 values. Okay, this is a fixed array. There's 3 elements in it. Okay, if I go to the code, you'll see. Okay, I'm set up for the fixed array. I'm just looking in that first slot. If I run it, in array 1, okay, look, look, everything is packed again because it was uint32, and that equates to how many bytes? 1, 2, 3, 4 bytes of information. It's packed them all into that one into this one spot. Okay, 3 again, it's saving space. It's just cutting off the zeros. It's only one leaf. Okay, here it is. RLP encoded again, as it's expected inside the Trie on the database. And but look what happens now. Look what happens if instead of the uint32 fixed array, now I put a dynamic array, and I also populate it with these values, but it can be populated with more values, right? It could be populated with more values. It's not fixed. So if I check that, look what happens. Slot 0. Okay, this is weird. We just have 3. We just have the value 3. That's it. And if you look, the storage root on our custom trie isn't equal to the storage root of our in process trie. Why is that? Because it's a dynamic array, and because dynamic arrays, dynamic information in a contract needs as much space as the user decides to add to it, right? Like you can push if there's a method on the contract that pushes information into the array. If if underneath the array I had actually added another storage variable, and that storage variable would be in slot 1. So how does Ethereum deal with dynamic information? What in an array, what this value is, this is telling you what the length of the array is, and to find those values, what you do is you hash the slot that it was in. So basically, so in code, what does that mean? In code, what that means is we hash. So instead of taking the 32 byte value of say zero expressed in 32 bytes, we take the hash of the value 0 in 32 bytes. Okay, and we look, and that's what we look for. That's the value we look for. We're gonna look for in the on the, via the provider to get the value back. Okay, so I'm still looking on slot 0, but I'm looking for the hashed value of slot 0. Okay, so now, okay, so we have two elements in. The first element was that one which had the length, and now at this hash value, we now have the concatenated values of that 32 byte 32-bit integers. Okay, so we had to go, and what, like, when I first started hearing about slots in a contract, I was thinking about an array, and I just thought that is weird. Like, how big does that array have to be to basically stick information on this slot, this number slot? Why it makes sense now is because what they mean by slots is places in the storage tree. So basically, this slot is a key inside a trie. I think it might be this one this time. I'm not sure if it's this one or this one. And if you follow this, it will take you to another node in the trie, probably with a leaf that has that value on it. So even though it seems like it's like really wasteful because like it has these slots with these massive numbers in, it's actually very, very minimal inside the database because of the Merkle tree structure. And then one last array. What happens if you put a 128-bit value? Okay, and I'm gonna try to rush through this. Uh, um, the 128-bit value, effectively, I'm just gonna tell you, because 128 bits don't, you can only fit two in each 32-bit packed slot. What it's going to do is it's going to do exactly the same thing. It's gonna start adding stuff into the hash of the slot value, and but then to find the next set of information for the array, you just increment the hex. So it's basically whatever that hash was plus 1 in hex. So if I basically add this now, all right, we have 3 elements. The first element is at slot 00. It now has 4. It has a length of 4, which is the type of stuff you can use. Like if you pull this back, you would know how many times you have to do this kind of hashing stuff to find all the values. But basically, but slot 2 is this hash. It has these 2 values, right? Data packed. And then if you see, this hash ends in 563. This one ends in 564. So it's the next hash number, the next slot, in quotations, and it has the other 2 values data packed. And if you look now, because we actually traversed all the information in our contract, our local storage root matches, I think it does, F5AC, F5AC. So we did all the stuff that we've been doing all this time, where we retrieve information from a provider or whatever, and we stick it in our own local tree to prove that the information is correct. But this time we had to kind of do all these steps. I'm thinking, like, basically, I think you can get the point. There's I'm gonna add this into the repo, but this is the layout state rules for storage, and this article explains to you all the tricks that you need to do of hashing, hash plus one, all that stuff, to find where storage where storage uh where storage variables are in a contract, inside the where they're located in the database. What kind of, like, computations you have to do in this way to basically find where they exist inside the Merkle tree, so that you can retrieve them. Okay, so basically, I'm thinking I'm not gonna show you the struct. You can go in it and you can look at it yourselves, because basically the struct, it's just more recursive of this type of rules. It's if you have a dynamic array inside of a dynamic array, you have to basically hash one of the hashed slots, and I think you can get the picture of what you would have to do. But basically, what's the big takeaway? Two things. One, for me, you know, when you start writing Solidity, I'm not a particularly experienced Solidity writer, and sometimes when you write functions, you get all these errors back where it says, like, you're trying to make a storage variable, but when you should be making a memory variable. The reason that is because, and the reason that you can only make storage variables when you are deploying a contract, is because the code of a contract is immutable. The contract itself needs to have those entry points. It has to have these slot entry points with which it can then, by itself, use these type of rules to traverse through the storage tree to either update information or to add information to it. But it requires you to declare your storage variables from the jump, so that the contract code itself can use them as the starting points to find where stuff is inside the storage tree. And just as one extra thing, this is also why mappings are so weird. A mapping, that, like, I will kind of show it to you in here, like, the to a mapping is to find where it is in the storage. It's the keccak hash of the information that you put in as a key of the map, plus where in the contract you declared the map, so that its initial slot. So what that means is you always need external information to be able to find where storage information is in a mapping. You can't just you can't iterate over information in a map. There's an external component that you need to add into it, that needs to get hashed to find where the key is in the storage tree to extract that value. So, for instance, in an NFT contract or something, it requires the address to be put in so it can get hashed. So inside the storage tree in the database, it can find where the key is to tell you what NFT data is associated to that address. If you understand. So basically, hopefully, I hope this was worth it. But for me, understanding how the Merkle trees on the database are associated to information or storage immediately started making me understand even assembly code a little bit better. It totally made me understand what the hell a storage variable is in comparison to a memory variable and all that stuff. And hopefully, like all that information about like the how it's all put into the storage tree, and how effectively like if we go all the way back, if you think about a block and a state root, and saying like basically I want to look at what the value was on a certain storage variable on a contract sometime in the past, and you would go to on the blockchain, and you would get to you would get that state root, and you would on the state root you would then give it the key to the address to that contract. As a result of giving it the key, one of the things that you would get in all that RLP encoded information was a storage root. Then you could ask for the specific slot you wanted, and then it would go off into the database. It would look at that storage tree at that root, at that state root, at that time on the blockchain, and it would give you that information. So at Eddie, who I think has left the chat, but he had said at one point, he had said, is it all like a giant dictionary? Is it all like a big hash map? And I was wrong when I said no to him. It is. And that's why this is how, hopefully, I hope that like I've kind of painted a picture to you of how basically the database, the Ethereum database with all its contract information, which is immutable, and these storage trees, how it's sort of like this one-way operation where you kind of you access it by giving the keys to the Merkle trees and accessing the information. And basically I'm done, guys. That was it. And I hope that round 2 put things into more of a blockchain context than the first one.
Yeah, mate, that's nice. It's like it's really like the rabbit hole's so deep in terms of like the optimization of storing data in that way. Like, is it? It sounds like it has multiple benefits, but I'm wondering of like what's the high level one? Is it about like?
Are we talking about data packing, or are we talking about just storage in the storage tree in general?
The approach to storing data in that way using tries.
Okay, okay. My takeaway was it's the idea that basically Ethereum in a clever way, because everything is kind of has to be what's the word, deterministic, right? Everything has to be deterministic, and for it to be deterministic, it needs to find a way to store information in a database. Say, for instance, with dynamic information, an array that needs to be able to be added to. It stores it in that hashed way that I explained, and because where basically the key gets hashed, and then you store information at that hash of the key. But on a tree, that information is super compact. Like, instead of thinking of it as this giant array of slots, and you're like, oh, I'm gonna put something at like this crazy hash number, and everything in between is empty. Instead of having that, even though it looks like that to the end user, at the storage tree level, it's just saying, put that hash as a key, and those values, put in on the storage tree, put this hash, put this value, and stick it into the database in this way, and that way it's super compact.
Yeah.
If that makes
yeah, it makes sense. It's like a different optimization, but thinking, I don't know if you've worked with like DynamoDB, and like the way that they've structured that database is like completely for like read and write performance, right, rather than like relational data or anything. And the result of that is like the query patterns that you have to do are like super specific, and the way you model the data is really specific. But I can see why the benefits of taking this approach in a blockchain kind of makes sense.
Yeah, because of its deterministic nature, everything is effectively everything is this giant lookup table where even this is something I didn't show at all. but it kind of, we can talk about it. When you instantiate a contract within a contract, you instantiate the contract by passing the address to that contract. And what the database does, or what the code does, it says, okay, I've been given a contract to instantiate. It's at this address. Node, go back through the state tree, find me the code hash, find me the code for this address, and then let me manipulate its storage by the kind of methods that we've been playing with. And it also has applications that you can start to think about this stuff in terms of proxy contracts and everything. But it all comes down to the fact that the database is secure. And hopefully you guys have an idea of, if you were a node, if you're a client, a light node, a light client, or a full node, how you would access that data. And also its deterministic nature, and how you continuously do this iterative lookup through all these tries to find the stuff that you want on the database. Is anyone there? Is anyone still here?
That makes sense, mate. I'm with you. It's like the concept of it being like an endless lookup table, like recursive lookup table, like completely makes sense in terms of like you might be doing a transaction on one block on the database, but like it's going to recursively need to do a lookup across the whole blockchain in order to get all of the information relevant to whatever transaction that you're doing.
Exactly, and I'll just add, not look up across the whole of the blockchain. The Merkle trees make it so that the path is direct, because of the keys. You know what I mean? Like all these keys we've been looking at, it doesn't have to kind of crawl through information. It just says, well, this is the information I'm looking at. In the background, stick it in a key. Stick it in a get method on the try, and give me the information that's at the end of it.
Yeah. So it doesn't have to traverse the database. It just gets that key straight away.
Yeah.
Cool, man.
So that's to the extent of my knowledge at the moment, that's basically that's what's happening behind the scenes, in Ethereum, as a program. Do you know what I mean?
Yeah, it's nuts. I just like, because when you think about databases and then I think about blockchains, I've never really worked with databases a huge amount, but I've got like a rough idea conceptually of how they work, but I'd never really bothered to think conceptually about how the blockchains manage all of that. It's super interesting.
Me neither. Me. Now, I've never done it before, and now after doing these talks, I'm officially calling myself full stack.
Love it. Brilliant. Awesome. So thank you so much for doing that. It's your plan to kind of bring together the reference material and examples, and then update that repo that people can refer back to in the future, right?
It's also partially updated, and just to remind everyone, if all the stuff is, I mean, it's really worth going off and reading about the stuff anyway. But as you read, I have littered all the commits with all these notes that kind of so hopefully all the commits with all the examples, there's stuff in there that can help sort of solidify the stuff that we've been talking about. No pun intended.
And you basically follow the commits chronologically, right?
Backwards though, from the first commit to the top commit.
Yeah, exactly. So the first commits to the first lesson, and then so on and so forth.
Yeah, exactly.
Dope, man. Awesome. Yeah, cracking work. Thanks again. Be interested.
Right. It was a whirlwind. Thank you for everyone, for the people who stuck around, first of all. And and I hope I didn't say like a million times this time around.
Nah, you're good, man. You have go and have a beer or something. I'm sure you're parched. That was really good again, mate. Well done. And I'll hit you up afterwards about getting the notes updated.
All right. Thanks everyone for showing up. And if I do a round 3, I promise that I'll make it more visual than this one, more like the first one. But yeah. All right. That was a long time. Thanks for sticking.
You did good, man. Well done.
All right, guys. See you in